All right, my name's Lawrence Papincak. I'm talking about the communications architecture for Project Icarus. All right, so the first idea that I had was point-to-point communications, pretty much using radio frequency based communications with two relatively large parabolic disks, one mounted on the spacecraft and the other mounted on Earth. The one mounted on Earth would either be on the surface of Earth or possibly in orbit, or maybe on one of the planets in our solar system, so just somewhere around here for that one. Second idea uses a series of relays. Again, we're using radio frequency-based communications, and what this does is we have smaller antennas mounted on many relays that span the distance between Earth and Alpha Centauri, and the idea for where these relays are going to come from is the fuel tanks that will be mounted on the exterior of the craft. And I'll talk a little bit more about that later. So pretty much the main importance of communications is data retrieval. We're going to be going to Alpha Centauri, we're going to be performing experiments, making observations. We need to get that data back so that we can analyze it and make groundbreaking physics, whatever, on whatever, Another idea that I had, SETI, if anyone's familiar with that, search for extraterrestrial intelligence. We're going to be 4.37 light years away. That's any signals out there are going to be way powerful than they are received at Earth. So potentially we could, while we're not communicating with Earth, we could point our antenna to other stars and try to listen for other civilizations. Summary calculations. There's a lot here. Pretty much I broke it down the hierarchy. Top is the most important to calculate. The bottom is what we're actually looking for. So without the top, we can't get the bottom, so it's kind of like a cyclical type thing. First one, carrier to noise ratio. That's we have the signal that we're sending, that's a carrier signal, and we change some property of that signal in order to designate a 1 or a 0. So the carrier to noise ratio is really important because that means for a given power of the carrier signal, if it's a lot higher than the noise, then we'll be able to easily differentiate the information we're trying to send versus the noise we're receiving. So higher carrier to noise ratio is preferable. We see just the equation that we use. Break that down to each section of the first calculation, the EIRP, or the equivalent isotropically radiated power antenna. What that is, that's a completely idealized antenna, saying that in the direction we're trying to point, as if all the power is going in that direction rather than being spread out into different directions and whatnot. So you calculate that, and then you subtract a bunch of other calculations from it to get the actual real value for your antenna. Free space loss, that's how much the signal is attenuating over a given distance. Where we have R there is the distance between here and Alpha Centauri. And one thing quick to mention, you'll see everything is in decibels. Decibels is just a ratio. It's an easy way to look at really big numbers in the range of 0 to like 100. Antenna gain calculation, that just involved the diameter. Again, in decibels, 1 over K here, that's just a constant, 1 over Boltzmann's constant. And you can see, just a quick example for decibels, K is 1.38 roughly times 10 to the negative 23rd. So 1 over that is something times 10 to the 22nd. But in decibels, it's 222. So I like to work with smaller numbers, so decibels are preferable. EB over N0, or the bit energy per noise power density. It's a big name for that one. This one's dependent on how many bits we think will be in error on average. And these values are usually calculated and theoretically and tabulated that you can just use for the given modulation scheme. And the modulation scheme that I've picked, QPSK, you're probably familiar with FM and AM, or frequency and amplitude modulation in basic radio. Instead of modulating the frequency or the amplitude, what this is, it's called quadrature phase shift keying. So we're actually modulating the signal by changing the phase of the sine wave. And that gives you better reliability and better information density in each wave, and I'll go into that a little bit later. Down to the real important calculations, obviously the bit rate and the bandwidth. Reformulating a lot of the decibels and turning it back into bits per second, we get this equation relating the carrier to noise ratio, the EB over N0 not, and then 10 is just one of the factors outside, and we can convert these calculations and get something meaningful out of it, which is our information data rate. And then dividing the data rate by the spectral efficiency, which is related to the QPSK modulation scheme, we can get our bandwidth. And bandwidth is just, how many signals can we pack and send out of a single antenna at the same time? It's the frequency gap that we have in order to do that. Quick list of some of the parameters that I've been using. Distance between here and Alpha Centauri, roughly 36,000 AU, or 63,000 AU. Relay to relay distance, roughly 500 AU. I got to this distance for the relays by looking at a few papers where they said the theoretical maximum distance of radio communications is roughly 1,000 AU, or the radius of our solar system. After that, the carrier to noise ratio plummets, and we can't differentiate communications from noise. That's just a theoretical value. So with that in mind, I said we have a relay, we have one every 1,000 AU. If one breaks down, then the whole entire communication link is broken. So I simply divided that by 2 to build in some reliability into the system to get 500 AU. Frequency that I've been working at, we're working with 12 gigahertz. That's in the Ku band of microwave. Why I chose that, I was working with S band, which is about 2.4 gigahertz. However, 2.4 is used quite a bit on Earth, where 12 Ku band is only strictly used for satellite communications. So there's a lot less chance for interference of signals using 12 gigahertz rather than 2.4 gigahertz. Freezing line there. RX gain antenna, that's the receiver gain. With this gain value, it's just a way to measure one antenna versus another. Obviously, a gain of 100, you're increasing the signal by 100, right? The power of that signal by a factor. So the higher the better. I have 73 in parentheses there. That's the current largest gain, or the largest antenna, the Goldstone antennas, antenna array out in California. That's 73. I think more realistically in 100 years, we'll probably have a gain of about 100 on our biggest antenna that we can actually point. And that gives you about a diameter of about 800 meters. So it's a pretty big antenna, but there are proposed designs currently in the works for within 100 years. Other thing, spectral efficiency, not too important. That's just saying that we have a density of 1.5 bits per cycle. So that's really good. Instead of just one cycle per bit, we have half, and that relates back to the phase shift keying. And then bit error rate that I've been working with, that's 1 in every 100,000 bits are incorrect, which is a pretty good assumption with modern technology. Down to the variable parameters, kind of where the goods are on this slide. We have the transmit power and the transmit diameter of the dish. These are what I've been changing rather than working backwards from saying this is what I want my bit rate to be, this is what I want my bandwidth to be. I've been working with how much power am I going to be able to get from the power team, and then deciding and telling you what the bit rate will be. So I've been using 10 megawatts for the point-to-point system, 10-meter dish, and I'm getting roughly 116,000 bits per second with the 77 kilohertz bandwidth, which is pretty good for communications at this distance. Just for comparison, I also did some calculations, basic calculations with the relay system at about 25 watts, which is a lot less than 10 megawatts, a lot nicer. And a 1.5 meter dish, which again is a lot nicer than 10 meters. We're getting a comparable information data rate and bandwidth. One thing to say about this is that you're using the same amount of power overall, but it's just decentralized. We're decentralizing the power into all these individual relays. So it's still a big challenge getting that much power over the entire system, but it's a matter that we don't have to generate it all in one spot. Moving forward, just further development of the relay designs, looking at necessarily like the physical design of the relays, of the fuel tanks, how we're going to incorporate the antennas into their design. And then again, just maybe some power restrictions, looking at propulsion system. Am I going to even have 25 watts to work with? Am I going to have 100 watts to work with? Just some basic calculations there. And then moving forward with the point-to-point, I've spent most of my time on this system. So it's really just about optimizing it, looking at, really keying in the power that I have, and then, getting out of that the desired bit rate. And again, just making the calculations more and more complex, fine-tuning the calculations down to something that I can be pretty sure of, more so than I already am. But yeah, so it's communications. Any questions?
Could you go back to the slide with, I think you had field parameters on it?
This guy?
Yeah. So that bit error rate.
Yeah.
What did you think you thought of that number? Was that?
That's tabulated. There's a few numbers, and based on some of the textbooks I've looked at, for the quadrature phase packet keying modulation scheme, that's a number that they use in a lot of their calculations, and based just upon modern technology. That's obviously if you use older technology or just different types of electronics, it's going to go up and go down. But then I guess an important note for the relay system is multiply this by n, where n is the number of relays, and that's your bit error rate, as you're going to have. This is bit error rate per modulation demodulation cycle. So if we have 126 relays to satisfy the 500 AU distance separation, then we'll have 0.00126 bit error probability, something around that. So it's not a number that I just pulled out of a hat. It's a common with modern communications technology. Excuse me, it's a common number to use. Just a good ballpark. Any other questions?
We might talk to you when the propulsion one comes up